A very good day to my lecturer, Dr. Mao. And today we get right into this Apex project, which is we are presenting and we are planning to do a hydraulic crane. Let's dive right into the introduction for this project. Hydraulic systems are widely used in various engineering and industrial applications due to ability to transmit large forces to small components. And so through this project we are aiming to show that hydraulics are widely used in daily life and real-world applications. The project focuses on design and development of hydraulic crane models to demonstrate the principles of hydraulics and real-world applications. The hydraulics principle is definitely the Pascal's principle, Pascal's law, which is very important for this project. As Pascal's law is stated as a force is always uniformly transmitted in an enclosed fluid. So, in all directions, this principle enables hydraulic systems to multiply force and makes it easier for input force to be very large output force. The problem statement of our project. The problem we are aiming to address is that nowadays hydraulic models are expensive and not cost effective. And so we are aiming to provide an affordable, functional, and easy to assemble hydraulic crane model for educational and demonstration purposes. Developing a simplified yet robust model bridges this gap, making hydraulic systems more approachable for learners and hobbyists. The objectives, of course. Primary objectives are to design a working hydraulic crane model using accessible and cost-effective materials to demonstrate key principles of hydraulics, obviously through Pascal's law, to evaluate the crane's performance in lifting small weights and assess its effectiveness as an educational tool, and to provide detailed instructions and materials to enable the replication of crane level.
Okay, now I'm going to present about materials and methodology. For materials, we use cardboard, syringes, without needles, plastic tubing, oil, glue, scissors or craft knife, popsicle sticks, rubber band, ruler, and pencil. We use cardboard for constructing the arm structure, syringes as the actuators. We need about 6 to 8 syringes. And then we use plastic tubing to connect the syringes for hydraulic movement. Oil is act as the hydraulic fluid. Hot glue or strong adhesive glue is used for assembling the parts. Scissors or craft knife is for cutting cardboard. Popsicle sticks is optional because it is just for reinforcement. Rubber bands is to add the flexibility or tension. And the ruler and pencil is for accurate measurements when we are drawing the blueprint. For methodology part, first we prepare the blueprint of the model as shown in the diagram. For the second step is to measure and cut out the necessary parts from the A4 cardboard based on the estimated dimensions. Then we should ensure the accuracy for the smooth assembly of the model. Then we should create a strong and solid base by gluing the cardboard layers together. Reinforce with extra cardboard or popsicle sticks for stability. For the fourth step, we should attach the arm and forearm pieces to the base using glue. Add spacers or reinforcements at the joints to allow rotational or bending movement. Then we should construct the gripper mechanism separately, ensuring it can open and close. Then we should attach the gripper to the end of the forearm securely. For the sixth step, we should fill the syringes with oil, which is the hydraulic fluid, and connect them using plastic tubing. Then we should test each connection to ensure the system is watertight and functional. For the seventh step, we should attach one end of the hydraulic system to the robotic arm's movable parts, which are joints and gripper, and secure the control syringes at the base. Then fix the tubing firmly to avoid leaks or displacement. The next step is operate the control syringes to test the arm's functionality. Ensure all parts move smoothly and make any necessary adjustments. To strengthen any weak areas, we can glue or add additional cardboard. And we can also customize and decorate the robotic arm if desired. That's all for methodology part. Thank you.
Moving on to the outcome and discussion. First, let's take a look at the function of hydraulic arm. The primary function, which is to lift heavy loads, where the hydraulic system generates sufficient force to lift and move heavy objects. Next is its rotational movement. Many hydraulic arms are capable of rotating at the base or joints, offering flexibility in maneuvering and handling objects from different angles. Next is precise positioning. Hydraulic arms provide fine control, allowing for accurate placement and movement of objects, which is critical in tasks requiring precision. And finally, gripping and manipulating objects. Hydraulic arms are equipped with specialized grippers or claws that enable them to hold and manipulate objects, which is essential for a wide range of tasks such as lifting and sorting. Let's then take a look at the expected outcome of this experiment. Based on the data, it shows that the force output increases proportionally with the input pressure, consistent with the Pascal's principle. This shows that the hydraulic arm works effectively within the tested pressure range of 50 to 200, but begins to differ at pressure more than 200 due to limitations on the hydraulic arm.
I will be presenting about the discussion and the limitations of this project, the hydraulic arm project. Alright, firstly, I will be talking about the material constraints as my first point. The plastic syringes and tubing restricts the maximum pressure capacity, leading to efficiency losses at around 200 kilopascals. The restricting of the maximum pressure capacity causes the prone of leakages and a lot of other issues for the structure. Secondly, the sealing efficiency. The non-effectiveness of the sealing from the syringes and the tubing will cause pressure loss. The minor leaks in the system contributes to pressure loss. Other than that, we have the durability. The prolonged use of these low-cost materials such as the lightweight wood, the syringes, and the plastic tubes results in wear and tear, meaning it will not last as long. And finally, we have the load capacity. The lightweight arm decreases the ability to lift heavier objects, and all of these as a whole, when the pressure is low, it decreases the capacity. That's all from me.
Hydraulic crane model provides an accessible way for individuals, particularly students, to construct and explore a functional mechanism using readily available and low-cost materials such as string, plastic tubes, and cardboard, making it easier for the learners to understand the fundamental concept of physics and engineering by actively engaging with the model. The hydraulic crane model can effectively demonstrate the principle of hydraulic, Pascal's law, and force of multiplication, such as when a syringe is used to push liquid through a connected tube, the pressure created is transmitted uniformly and allow the model to lift small weight, even with minimal input force, while clearly illustrating how force can be multiplied in hydraulic system. Lastly, the crane model serves as a practical and interactive educational tool for understanding real-world application of this concept, and also can simulate how hydraulic cranes are used in industries to lift and transport heavy material, while the student also can relate its mechanism to larger hydraulic system found in construction, automotive braking system, or even aircraft landing gear. Thank you.